Hello, today's lab is on heat of combustion. We're going to be burning some ethanol, denatured ethanol, and when we burn it or combust it with an oxygen, it's going to produce water vapor and carbon dioxide. The results on this lab are not great. There's like a huge margin of error for this one due to the nature of the experiment, which we're going to look at. But it's still a nice, fairly quick experiment to run, and there have been questions on this type of experiment on the AP exam in the past. So it's a good one to make sure to do with the students. For the procedure today, I've already measured out 100 milliliters of deionized water, and I'm going to add that into the soda can. And you want this to be fairly accurate because we're going to use that 100 milliliters in our calculations later. And then in the alcohol burner, you can see that there is a cotton wick and a little ceramic like cap. But in here there is ethanol, and it is denatured ethanol, so there is like an agent in there that prevents people from drinking it, but it is denatured ethanol, so the ethanol is soaking up into the wick. And you should have students record the mass of this whole thing before you start. So we have 218.40. And then you should also go ahead and record the initial temperature of the water. So it looks like it's 24.4 degrees Celsius. Now you want the temperature to change by at least 10 degrees Celsius. What I usually tell students is it's easiest for them to track the change in temperature. So if you make sure that it goes 10 degrees Celsius higher, and then you can blow out the wick and then record the change in mass of the alcohol burner. Okay, so the temperature of the water changed by 10 degrees Celsius, and then I put the burner back on the balance, and so you can see the mass is now 218.02 grams. So some of that ethanol burned and changed into carbon dioxide and water vapor. There's a few sources of error here, of course. It's not an insulated system, so a lot of that heat is lost to the surroundings. And another error that can pop up is that if the temperature probe is right up against the bottom of the can, then it will measure a lot higher temperature than if the water itself was mixing better in the aluminum can. Try to get students to kind of mix with the temperature probe or with the thermometer, and make sure it's pulled up away from the bottom of the can. So again, here's the chemical reaction that's happening. We've got ethanol burning in air to form water vapor and carbon dioxide. You'll see the mass is decreasing over time because some of the ethanol is reacting and turning into two vapors. And so those will evaporate into the air. Now we used 100 milliliters of water because water's density is 1, that's like 100 grams of water. And we blew out the flame when the temperature changed by 10 degrees Celsius of the water. So using our Q equals MC delta T, we're going to use that 100 grams of water. We'll use the specific heat of water, and the change in temperature was the 10 degrees where we stopped the reaction. And so when we multiply there, you'll get joules, 4,180 joules. So that's the first part. That's the amount of heat that we measured was released. Now, in reality, it's probably a lot higher than this because it lost some of the heat to the surroundings. Not all of it made it to the water inside the can. But that's our calculated value for this experiment. Now, to get then to a heat of combustion, we need the moles. So the starting mass of our alcohol burner was 218.41, and our final mass was 218.02. When you subtract, you'll get that 0.39 grams of the ethanol burned left as the water and carbon dioxide. I want to change grams to moles using the molar mass of ethanol. And so when you divide there, you get 0.0085 moles of ethanol was burned. Then I can take these joules that we found, change that to kilojoules, 4.180 kilojoules, and divide it by the moles. And I can just use the moles of ethanol directly because there's one ethanol for every one reaction. So it's the same number of moles of ethanol as the moles of reaction there. And when I divide, I get 493 kilojoules per mole reaction. Always remind students that they're not done yet. So like this is your heat released. This is our calculated kilojoules per mole of reaction, but you always make sure to double check the sign by the end of it. So because the reaction was releasing heat that caused the temperature of the water to increase, this value must be negative because the process was exothermic. So this is our experimental heat of combustion, negative 493 kilojoules per mole of reaction. Now, the true value, the heat of combustion of ethanol, is negative 1374 kilojoules per mole reaction. So you can see that the error there is very large, but it's an expected amount of error. Do you see how our experimental value is much lower in magnitude than the true value? Well, that's because a lot of the heat was lost to the surroundings. So if all of the heat made it to the water, you would expect this temperature change to be much larger, which would mean our Q should have been much bigger, and therefore our heat of combustion should have been larger. So we talk about those errors as you go through the calculations and following those through to the end. And we can talk about why this value is so large. I also ask students to give a couple possible ways that they could reduce the error for this, but still keep it to a safe experiment. So we always get some interesting results from that. But yeah, it didn't take too long to do this experiment. Sometimes I'll have them do multiple trials and find an average, or we'll find a class average. But either way, you're not going to get the best results. But it's a good one because you'll see questions like this on the AP exam pop up once in a while.